Welcome, Cristina Sardón from Universidad Politécnica de Madrid. It is a pleasure to have you here. So thank you for your talk that you are going to give us, and you are going to speak about from Dirac to Dunkl operators through symmetry-reduction. Please, the floor is yours.
Thank you so much for having me. It has been a couple of years since last time I was at Coxeter, so I'm happy to be back. I didn't know what theme I could choose to have a wider audience, so this thing kind of has a little bit of representation theory, a little bit of operator theory, a little bit of quantum mechanics, a little bit of everything. So I thought I'm gonna make it like very easy with a little bit not historical explanation, but what other authors have done, so you can get like a general feeling of it more than going into depth into real theoretical aspects. And I'm not gonna give proof. I'm just gonna give some statements, and uh, I will expect you to believe them. But I have the proofs on the archive if you want to see them. So I always like that, like to make it easy. So everybody can follow along. So I'm going to talk about the arc operators that I guess you know, and I'm going to talk about Dunkl operators that I know so well. Dunkl operators are something relatively recent from the 70s, and there are some operators that are just a deformation of a Dirac operator. You will see that the deformation is something related to reflections, to a group of reflections. So what we want to see is how to get from a Dirac operator to a Dunkl operator. There's several ways to do it. One of the problems of one of my postdocs was to solve something called quantum reduction of the Dirac operator to get to the Dunkl operator. I was never able to do it. I hope there's someone who is an expert with representation theory that can solve it for me. But I have solved it somehow differently. You will see just with some main ideas. So I've gone from one to the other, not in the expected way. There's still that open way to get there. So yeah, I put this on the archive recently, and since it was a different way to get it, it was interesting. And I got an email from Dunkl, who's an emeritus professor, the very same day. He said, Christina, I really like it. It's an interesting thing that you got to do this. I'm like, okay, I think it's worth it. So it's just interesting. So I'm going to tell you what it's about. So Edwin Goff is a professor he's in MIT. And he's the one that I was reading the seminal papers to actually do this reduction from Dirac to Dunkl, but I was not able to do it. But what he did initially is that he would take the cotangent to the general linear group. And what he did, which is basically equivalent to getting like a free Hamiltonian or free space. And he would perform something called Hamiltonian reduction, which is just taking a quotient. You have to get like a momentum map and quotient in the orbit of this momentum map. And for this Hamiltonian reduction, he would get to something called the Calogero Moser phase space. So basically, he was able to get from something like a free Hamiltonian, he would get this Hamiltonian of Calogero with this extra term that has like a kind of interaction coming from a potential. It can be interpreted as particles interacting in an inverse square potential. So his result was to get the Calogero-Moser dynamics arises a Hamiltonian reduction of the free particle motion, okay, in the cotangent to general linear group. And in the quantum picture, how can you do it? Well, in the quantum picture, you will get a free Laplacian, which is would be the equivalent, and you will reduce the free Laplacian to the Dunkl Laplacian.
Was capital P any specific vector field or?
This,
Yeah.
well, it's related to this momentum. I can show you later for this. It's just a matrices with momentum, something like that in some cases. So the quantum counterpart will give this free Laplacian to Dunkl Laplacian, and this was done. So you have it in the classical sense, and you have it in the quantum sense too. But what happens with the Laplacian? Well, the Laplacian is a second order operator, right? And you will get to another second order operator that will have some kind of terms of this kind. So the main question was if you could do it at the level of first order operators, right? Because you know, if you have a Dirac operator and you square it, you will get the Laplacian, right? So there is something called the Dunkl Dirac operators, and the question is, if I square the Dunkl Dirac, will I get the previous one? Right? He had this Dunkl Laplacian, right? So what happens that here you're working with operators that were second order. You're just going to first order, and what happens in the first order that you are dealing with the square root, which is a problem, right? So then you have to realize how to use that square root, and you have to go into a Clifford algebra to realize that, right? So that's the problem basically. Is this reduction in the first order level through this Clifford algebra that are going to specifically start taking a role in there. So that's the problem basically. So the main objective is this. So we had a free Laplacian, a Tinkoff's reduction gets to the Dunkl Laplacian, which is another Laplacian that's going to have an extra term, which is a deformation that I'll show you more specifically. And what happens? The Dunkl Laplacian also, when you square it, you are going to get something that is the Calogero Moser Hamiltonian that is really welcome for that interaction. So what we want to do is the free Dirac. We want to do a kind of reduction in the linear level here with first order and get to a Dunkl Dirac operator. And with this, when I square it, I want to go back to here. Let's see, commutative diagram. Okay, so I think that proves the reduction at the Laplacian level, which is scalar, right? But I'm trying to look for this interpretation at the Clifford Dirac algebra, which is like a little more complicated in that sense. So how do we start? Well, so initially the problem to do it, this reduction, you will have to use quantum reduction basically. So during this, in the way I think of it for the Laplacian, if I want to do it with Dirac, I will have to have an algebraic framework in Chernic algebras. I will have to have operator algebras and invariant. I will have to push them by the quantum momentum map, right? I try to get to the operators, and then you will have to try to get to the Calogero problem. So this is the nature is representation theory, right? So which is I don't know. I have done it, but only for SU2. I cannot do it for higher. I don't know how to do it, but so what I did an analytic realization. So what I start with is a Dirac operator on a ring chamber, and what I'm gonna try to see is that this Dirac operator in the chamber has to be a skew adjoint. Okay, and also by imposing that this Dirac is gonna be a skew adjoint in the ring chamber when I reduce. So I call it reduction too. It's not quantum reduction, but I'm reducing to the positive part of the chamber of the group, of the reflection group. I have to get that this reduction is going to be skew adjoint. Also, I'm going to have some kind of boundary terms when I'm integrating in boundary. So I want to get rid of those two. So what I'm going to do is call something drift that's going to come from being self-adjoint on the chamber, and I'm going to get something which is a wall contribution, which is the boundary analysis on the boundary. You will see. So with these two things, when I compensate them, I get to the Calogero Hamiltonian that I was expecting via the boundary drift. So basically, I'm not using representation theory, which I'm sure is possible to do, but I'm using like a functional analytic and geometric points. So I'm going to show you what are the steps to do. So again, so this is the detour that we take. Like Dirac operator, I want to get to Dunkl Dirac operator. How do I get here? See that here you just have a Clifford algebra and Clifford algebra and partial derivatives. And what I have to get is this. You also have the Clifford algebra, the elements. I will go into more depth of this elements now with operators determined. And with the partial derivative, this is an extension of the partial derivative with some deformation. So here I have two steps: the valve chamber, and I have the analysis of the modifier theory. So I'm going to show you first the Dunkl operator, because I'm talking about an operator that has some kind of deformation, but I haven't told you anything about the deformation. So here's the deformation. So I'm going to call tilde. I've been kind of using notation as well, and sometimes only T. I have to fix a little bit this slides, but I'm calling with the tilde when I'm not using the Clifford elements, okay? I'm just here using the scalar. So C, this would be Dirac, which is the directional derivative, but I have this extra term. And what is this extra term? Where this extra term comes from reflection group. Okay? So imagine, let's start with a flat operator. So we are going to start in Rn, okay? And it's defined in this way. You can define it also in Riemannian manifolds. That's something that I'm looking at right now. And S is going to be the reflection across these planes. Okay. So, and these are the roots of the reflection group. You can do it in several reflection groups. I'm going to show everything in AF. Okay. And as specific examples, A1, A2, which are going to give us Calogero. That's the most important one. But you can do it in other reflection groups. Okay. Let's see that when the parameter K alpha, which is the multiplicity function that controls the strength of the correction, let's see what we get back to our Dirac operator. So wanna get some kind of insight about this extra term. Okay. So see, this is the function. You put x. This is the function in the reflected for x across the plane defined by the root alpha. So these are called Coxeter groups. They are finite groups. And what we are going to do, well, is also a subgroup of the orthogonal group. So each reflection that I was telling you is defined by a root alpha 3, and it's fixed in the hyperplanes in which one. Like, okay. And you're going to have a set of roots, and it's going to form a root system. And always the root system becomes each of the positives and the negative roots, which is something that I'm going to use. So a choice of the positive roots is going to determine a fundamental valve chamber, which is what I'm going to restrict myself to. So the Dunkl operator is basically this, the operator that goes into the directional derivatives but these reflections. So I guess that you know about this, but I want to do it easy. So the Coxeter group, let's do the A1. Okay. So the A1, it will be the one that is acting on the real line. So what would be the chamber? Well, I'll take the 0 and I'll take the positive part of the real line and the negative part, and I'm just going to take the real part. So see that this always is the reflection. When you get alpha equal to x, you will get minus x. So I'm just taking negative points in the real line to the positives. That's the fictitious reflection that is given by the A1 group. So this group has identity, and it has the operator S, which is basically just changing the sign. Okay. What will happen in the A2? A2? A2 first. What will happen in A2? Well, in A2, we'll have a root system in R3. And we're going to have a slight exchange of the positions. It's basically A2 is S3, is the symmetry, the permutation group. So, have any vector can be written as this in R3. And what happens is that the root system is going to link in this plane. Okay, the roots are going to be the finite differences of the basic vectors, which I'll just take to different bases. That would be the roots. So each reflection, the S is just going to exchange the component, the 1, 2, 2 by 1. And you have, how many reflections you will have? You will have 6. I'm just taking the positive ones here, which is what I will restrict to. You will have these ones with plus minus both. And here you have the positive ones, and again, and each reflection, which is going to the hyperplane after changing I by j. So I'm going to show you how to write the Dunkl operators in A1 and A2. So in A1, it will be easy. The direction of the orbit will be only differential with respect to x. And the reflection will be taking the function on x. K is a constant. And here, it will just change the x by minus x, basically. And this is the extra term. Again, what would be the Dunkl Laplacian? Well, the Dunkl Laplacian, you will have to take here, this will be taking the element of the Clifford algebra. I'm not using a middle notation. Do square of this one multiplied by the element, and you will get the Dunkl Laplacian, which is basically terms of the Laplacian, but you have these extra terms that are giving you the correction for the equations here. Okay, so as you can see, Dunkl Laplacian is just a modified version. If you want to do it on even functions, this basically simplifies to having this extra potential term. And also how it can be defined from the point of view of the Calogero Hamiltonian. Well, again, to get the Calogero Hamiltonian, you just need to do a H transformation of the functions that you are operating on. And if you just do this change, you will get exactly the Calogero Hamiltonian. That is what there is. So you know where it comes from. And also you can do it in A2 and of course in AR. So it's visible. In A2 you will have three components, and you will have to get the Hamilton, the Calogero Hamiltonian, you will have to get each of the components squared and sum them, all of them together. So these are each of the components. So in all the directions, in x1, x2, x3, that's the extra terms with the changes from 3 to 3, etc. You can see it's like that can change the positions. That's where you have all the permutations of S3. What they have, these operators, where it's giving you some kind of integrability hint, is that they'll satisfy that they compute. So if these ones you square them again with the Clifford algebra and sum them, you will get the Calogero Hamiltonian after the H transformation. Well, you can do it, right? So you square them, and you get this Dunkl Laplacian, and leads to the quantum Hamiltonian. Just doing a little bit of H transformation of the functions. So basically, these Dunkl operators that I'm showing you in A1 and A2 are unifying permutation symmetry, in this case in A2, some differential structure, and inverse square infractions. So here you have some inverses. Now you have a quantum Hamiltonian, so you are operating over functional space, that is the quantum space. You have some kind of reflection symmetry, so you have a little bit of group theoretical. And we're going to go into the more analytical part, which is basically doing integration by parts to get the skew or joint characters of these operators.
Excuse me, could you remind me what was the K?
The K?
Yeah.
The K is just it's a constant that comes from the interaction of the reflection terms. So this one. So depending in A1 and A2, the constant is the same. It's K alpha. It depends on the group.
Okay, it's any real number.
Okay. Yeah, in this case, yeah, it's a constant related to the group. So in A1 and A2, it's just it's a scalar. Okay. In other groups, it depends. For us, it's just actually, it has a physical interpretation that is related to the strength of the potential.
Because from the formula, looks like it was an integral. K minus 1. No, well, the following in the Hamiltonian, in the quantum Hamiltonian there. K times K minus 1. It looks like it should be an integral or something.
No. It's just it's a constant.
Okay.
Yeah. That gives you the interaction. In this case, yeah. In others, no. In others, it's a function. Actually, here when you see it, this is related to the gravitational potential. So this can be written in terms of the potential. Data you're seeing is an interaction of particles in a gravitational field. You could see an interaction of particles in a Coulomb field. Also, it could do the strength of the Coulomb potential too. So they're related. So that's what I told you. So if you write the A2 Dunkl operator, it will also be a constant. It will have any change. If you square it, also this will be the Dunkl Laplacian, and this case, the one that is actually like defining how this is formed, right? The deformation from the single Laplacian to the deformation. So by the K, I measured the deformation, which is all these terms. When they are zero, this K it disappears. And in A2, I restrict to symmetric functions again. I was getting this, which is the almost the Calogero case if I do the gauge transformation. So those are the Dunkl operators. So can you write the Dunkl operator in other groups? Yeah, E2, E2, the groups, exceptional groups. So the Coxeter groups have the Dunkl operators, but I haven't checked them because what I wanted to see was the Calogero Moser one. And I know that I get it from day one, so but the other ones can be expected and what they give. Similar. So now that you know what Dunkl and which is Dirac and how they define, just the goal is to derive the Dunkl operator from first principles that you will see, which is just imposing a skew or point and some kind of reflection on the boundary. And you will get this Dunkl operator from the flat Dirac operator. Is what you see. So how do I start? Well, the flat Dirac operator is just defined like this, which is the directional derivative, and these are the elements of a Clifford algebra. So that's a commutative algebra, the usual one that's using quantum mechanics and the generators. It's a real Clifford algebra. Satisfying is RT. Okay. In the Dirac, it's going to act where? Well, we are here in quantum mechanics, right? So when you are using a Dirac operator, what happens? That we are not in functions anymore. We are acting on spinors, right? It's a spinor value functions. Because here you have this. So we pass from functions to spinor value functions, where S is the representation of the Clifford algebra. Okay. So if you see this is Dirac, I'm going to square, as we said, we will get the Laplacian. So now, how do we, so starting from this flat Dirac operator on our end, we're going to review just a little bit of some properties of the Coxeter group. So when you have the Coxeter group, it's going to act like the orthogonal group, okay, of transformations. So it's going to take an element, and it's going to go by the element of the orthogonal group, change it. Then also we will have a spinor representation. So how does the spinor representation? Well, the spinor representation is going from the Coxeter group to the spin representation, which is in the Clifford algebra, and it's gonna have the usual spinor property. And also the combined action on the spinor field from the flat space to the spinor, which is gonna give us just this operation. Okay. I will use that for generalization after. With this action, then the Dirac operator has to be equivariant. This is going to be important because I'm going to pass from chamber to chamber, so I'm going to have some equivariance in the loop. So I will impose that. And then what I have to do is that when I restrict to the fundamental chamber, we're going to have this boundary chamber. So I will use some of these properties afterwards. So now, you know how I define Dirac? Now this is Dirac. Okay? So Dirac was the same thing, but this was the directional derivative. Right now we have changed the T, but these are the Dunkl operators that we have defined of the reflection group. Okay. So how does this work? Well, without this would have to also go into spinor because we have get the Clifford algebra. So over a function that's gonna have values on the spinor, just gonna have here the Clifford algebra and the t. This would be tilde. I'm using notation, but I told you because it was I have to change. Maybe don't upload the slides until I make this little correction. It will be t tilde. Okay, because this will be the t, the complete t word. Okay. So that's how it will work on the spinors. So let's do two things now. So we start with the flat Dirac, okay? And then what we're gonna do to see these symmetries is restrict the flat Dirac operator to a single fundamental chamber, and then redefine the scalar product so the operator remains skew in the chamber. So those are my major steps to go from Dirac to Dunkl. And this is what is gonna change. So initially, the flat Dirac operator, it's defined on some functions that are defined on the spinor. Going to take values on the spinor and they're square integrable. And now we're going to go from Dirac-Dunkl operator. How are we going to change this? Well, what we're going to do is that we're going to act on functions that are square integrable, but we're going to have to change the measure. Why do we change the measure? Because we are restricted to the right chamber, the positive one. So that's what happens. That's going to be the new measure. The initial measure was the best measure in the whole space. Now restricted to the fundamental right chamber, we have a new measure that we are going to use. So that's a key point in the whole thing.
Basically, the measure that you had at the beginning was Euclidean, I guess.
Yes, because I was on the flat space, and now we're going to have this Opdam measure, which is the standard one. So this is the measure. So this is how I realized that maybe I could do something with this. Because I was reading something randomly, and I saw something of reduction to a fundamental chamber introducing this weight. But this weight, you will see now that when you take the derivative and divide by it, you exactly get the extra term of the Dunkl operator. That's when I realized, after years, because I was trying to do this problem in 2019 with the representation theory, I was like, I don't know how to do it, so I just left it standing. One day I was reading something that came out in group theory, and I was like, oh, okay, so when you reduce to the fundamental chamber, actually you have to introduce this measure. And so this is precisely the term of this reflection thing. So that's what I said, okay, maybe I can do something. So this is what happens. So when you restrict to the chamber, you have to change the product. So to do the product of this space, this silver space, you go, you have to do the interval in the chamber. You have to introduce this measure to define the product, and this is the measure process, the positive part of the chamber. So what happens? That now I have a new space where I integrate. So these functions are going to be square integrable. And also, but just restricted measure. Okay. And here, see, if k equals 0, you will get it again as measure. So that's the difference. And it's precisely the k of the reflection group. Okay, so initially the flat case, when you have Dirac and you have the Lorentz measure, what goes wrong? Well, this is imposing that the product is skewed, right? That's the definition. What happens? Well, that when I go to the chamber, it's no longer skew joint. So what I have to do is to make it skew joint in the chamber. Okay, so that's one thing. So we're going to force that. Okay. So with the new, let's call it weighted linear product, this fails for two things. This extra term, which is what we'll do here, and we're going to introduce, and also the Weyl term, because when I am here, also there's Weyl terms there, right? You are supposing there's 0, but you're supposing really good functions for quantum mechanics, they dictate, so wondering Weyls. But now you have to take out the Weyl terms and you're changing the measure. So we have two problems to be compensated right now. So the first one, if you want the operator to be skew adjoint on the chamber with the new measure, you have to add this term. I'm not going to give proof, but you can check it out on the archive. So if I do this, this logarithm of the weighted measure. See this precisely. It's the term that I was looking for. This is what I saw. So I said, okay, I think I know where it comes from. So now that's gonna come here. So if you do this deformation to the partial derivative with this, you are going to be able to compensate that drift that was breaking basically the skew adjointness of this middle product. So that's one thing. No proof, but believe me, I have proved it. That's one thing. And then we are gonna put that little extension into the directional derivative. We get to is almost a skew adjoint. What is now missing? That there's a boundary term. So how can I get rid of this boundary term that are appearing along the hyperplanes? So this is the almost skew adjoint. Having to do it on the chamber, and it will be with respect we measure skew adjoint instead of boundary term. So I'm gonna take out the boundary term. So that's the work contribution. I have to see with the reflection. So I wanna cancel the reflection. So how do I do it? Well, so basically the reflections, what I'm doing is just mapping one chamber to the neighboring chamber, right? So in the weighted measure, as I told you, you have to see that it's gonna be equivariant of the chamber. So that's what I'm going to use too. So the weighted measure is gonna be equivariant, so I can do it, I can make a change. The reflections are orthogonal, so when I'm making this change for the proof, when I'm making this change accordingly, the determinant is -1, and I can do this change. You can see all the details if you want. So this allows us to integrate over the whole space. So basically what I'm doing, I have reduced to the chamber. Now, okay, I have to take out the boundary terms. How can I get rid of them? Well, I'm just gonna go on instead and take them to the whole space. So I don't have a boundary. So what I have to do, I have to pass through the walls. So by that, I have to integrate the whole space. So this is where I'm using the equivariance. And now what I'm doing is instead of going from the chamber, I'm just adding the extra terms to go to all the space. Basically, these are the things that I can do. You have to do a few integrals, and you can integrate in the whole space. Okay? And you will see that you can actually get rid of them by introducing this extra. So far, we have introduced that just from the skew adjoint. And now to get rid of the boundary term, I have to do the function at this point, but I have to rest the reflection. So now if I add that extra just by hand, and I do the computations again in the new measure, in the whole space, the product is skewed. So we have compensated. So basically, I just got two things. This, that cancels on the bulk drift in the measure, and now this extra term that's gonna cancel with the reflection part when I go from the chamber to a whole space. So this results formally in skew adjoint on the measure. That's how it's done. So basically, one can interpret this. So basically, one can interpret this Dunkl operators as just a deformation of a Dirac operator, changing the measure, going to the chamber, and then adding the reflection. That's what's happening. So we prove it for T. This will be tilde, because I'm not adding here in this thing. I haven't added yet the Clifford algebra. But I'm going now, it's going for the whole Clifford, which was TK. But we know that each generator of the Clifford algebra satisfies skew adjointness, right? So when I multiply, since the whole Dirac is just formally the sum of these things that are proven with the E, it's easy to put that. Dirac and Dunkl skew. Well, those are the properties, and also when you square it, you will get the deformed Laplacian. And you can say, well, why is this interesting? Well, usually the Laplacian you get to lots of harmonic analysis, right? The Beltrami operator. So here, it's basically a deformation of that operator. So what is this operator is going to give you? Well, they're going to give you a whole harmonic analysis that is different from the Beltrami Laplacian operator. So also, I guess that for analysts can be of interest.
But I mean, you have overcome the problem of having these walls, but still the walls are still there. I mean, is there any difference of value of the operator when it is crossing the wall? I mean,
yeah, when I don't have the wall, I'm missing still an extra term from the Dunkl operator.
That extra term.
Yeah, but if I put, there's no wall, because I'm just taking the zero wall, for example, in the first case, I'm using the whole space, it's just putting the reflection around all the values.
Yeah,
by adding that with that interpretation, you're back. And integrating all the boundary terms are gone. Okay, so I pass from chamber to all Rn. That's what I'm doing. Okay. And also, yeah, so it has interesting things for harmonic analysis because you have that all the individual parts commute, all the components of these T's. So basically, you have like a whole open thing about this Dirac Dunkl. And now, if you want to go towards global equivariance on the group, well, see that those were first depend only set it in the chamber. So I have to do something, and then we're extending the whole integration to the whole space. Okay, so what we have to do is to introduce like our global equivariance for these spinor fields. Okay. So you know that the spinors they also have the equivariance across this wall. So this is the only thing that I have to close with a representation. So I'm taking the unitary representations that commute with the Clifford action, and what I'm doing is now do this global thing for all the figures in space. So yeah, we have to introduce a representation, and depending on the representation, you will have different kinds of operators. So that's what I'm just going to show you now. First, in the scalar case, it will be the standard operator. For now, you will have some others. So this representation is basically like twisting of the reflection by a unitary transformation. And this is just a little summary. But let's see explicitly one case. So let's do the A. So we're going to take a direction, put the directional derivative, and let's choose the canonical vectors in A1, A2, A3, which is going to be the alpha 1, 2. And so you have positive roots, you compute the brackets, okay, you get these things. So the Dunkl operator, for example, in this direction, you will have the partial derivatives in the direction x1 x2, and you will have the terms. In this case, I think these ones are also constant. I don't remember if they are the same at this level. I will have to look into it. And when you do the computations, the first part, you will have the station with 1, 2, and this are flipped. And this would be the component, for example. You see it. So you can get different representations. So you have the trivial one, you get to the usual Calogero, which is the Calogero Moser differential wave transform. And there you have it by taking the trivial representation one. If you take the sign representation, it's basically the same but with the opposite sign. So this is called the odd antisymmetric Calogero type operator, and the other one is the symmetric, right? And it would be it's called bosonic. No, this one is the fermionic. Saying the opposite, right? And then you can take a two-dimensional representation, the reducible one. So now see that the function is actually a spinor, has just two components. You can take a representation. For example, this one, you can do the calculations. So this would be like a generalization of the Dirac operator in this direction. And here you see more of the spinor character, right? So there it is. And these ones, when you multiply by the elements of the Clifford algebra and square, you will get the Dunkl Laplacian. Same way. Okay, you want to see some geometrical interpretation. So the denominators are measuring the distance of each reflection to the hyperplanes, while these matrices are implementing internal symmetry of the two-dimensional representations. That's 3 in this case. And in the scalar case, in 1 and 2, the matrices reduces to 1 and 2. So you have the scalar cases of even at Calogero Moser operators. The ones that we wanted to get. And that's what I wanted to tell you more or less. Questions?
I have a really ambiguous question. Because you produced the symmetric operator, but it has three representations. In fact, you use the second one, so you get a third symmetry. So is it possible to get a symmetric operator, but in the sense of that third symmetry?
Probably I haven't tried. But yeah, I think you can write it down. I think so. Yeah, I just hinted at the ones that were giving me Calogero, and I just wanted to write two, like a two-dimensional one, just to show it. But I have never seen those one written down. I had only seen the scalar types. And I said, well, let's write it down and complete the square and actually. So probably. Any more questions?
There is no more questions. Thanks for speaking again.
Qué calor, ¿eh? ¿Cuánto he tardado? 40 minutos.
40 minutos.